Okay, in this chapter we're going to be looking at organometallic compounds. Now, where this comes in really handy is it's a way of making actually new carbon-carbon bonds. It's very useful because technically to create that new bond, we're actually going to have a situation where one of the carbons is acting like a nucleophile and the other one is acting like an electrophile. Very much like this. So typically, when we actually have seen this type, or our reactions thus far, we've actually had our organohalide, where the carbon acts like electrophile, and then we just do nucleophilic substitution, SN2 or SN1. Any of our substitution reactions, we had nucleophiles attacking the electrophilic carbon. All right, so what we're going to do in this chapter is introduce a tweak. What we're going to do is attach the carbon to something that actually makes the carbon more nucleophilic, and therefore it attacks the electrophile. And where this can really be cool, it really can be that this carbon, that nucleophile, attacks a carbon that's an electrophile, making a new carbon-carbon bond. All right, now the trick of this M trying to kind of gives it away. So what we actually need to get the carbon to be nucleophilic is something that's less electronegative than a carbon. And on the periodic table, there aren't many things non-metal-wise that are less electrophilic than carbon. Matter of fact, it's just boron. So what we end up doing is using metals. Now, all of these are ones that have actually been at least tried and used. And we are going to see that there are a few that pop up a little bit more commonly. Matter of fact, we actually don't use a lot of these, but they've just been investigated. We're going to look at our main ones that we have chosen to use over the years to create these coupling reactions, these R to R new carbon-carbon bonds. All right, now first of all, let's get over the naming of these. Now, naming of an organometallic is relatively easy when we realize that they are, for the most part, just common name like. And what I mean by that, we almost always name the R group as if it's a substituent. So butyl, ethyl, propyl, and there's ethyl again. And then we say what metal they're with. So butyl lithium, ethyl magnesium bromide, propyl cadmium, and it's di because of 2, so dipropyl cadmium, and ethyl, but there's 4 of them, so tetraethyl lead. And that really is the trick. Now, when they get a little bit more complex, when we can't name the substituents quite so easy, it changes this some. But we really don't bother with that too much. Right now, we're just going to be naming them kind of like this. We're not going to get into the crazy advanced naming with organometallics at this point. All right, so let's look at our earliest ones that we actually did for these coupling reactions. So, and rather than actually show the reaction, we're just going to show how we make the organometallic. And the first one is making them with lithium. Now, biggest reason this is done is because it turns out the organolithiums have a relatively good shelf life. That's our products in this case. You actually can buy, in a lot of cases, these chemicals with the lithium already attached. You don't actually have to make them. That can be kind of nice. But if we ever do need to make them, you actually can just take an organohalide, treat it with lithium, and you're going to get your organolithiums. And it does it relatively easily, relatively safely. These are all kind of exothermic, so you have to watch out for that. But these are very easy to do reactions. Hexane is the solvent of choice. Now, earlier than that, and ones that create slightly better or a little bit more stable final products is the Grignard reagents, which is where we're doing the same type of thing, but we're using magnesium. Now, specifically, it's magnesium turnings. Now, our problem here with this one is that water, even moisture in the air, has a very good chance of breaking down your components. So this is not very stable around water. So, and even in making them, we end up using diethyl ether or THF. THF was tetrahydrofuran, so it's a ring with a single oxygen. THF is slightly more shelf stable, which is why it's used a lot more. Turns out diethyl ether will form peroxides with itself, and that actually makes it a flammable and explosion hazard. Now, if we have it in the lab, it's got stabilizers, and it's not like you have to worry about a bomb blowing up the whole building, but it actually doesn't have the longest shelf life. THF is a little bit better. But both of these, so the magnesium, the Grignard reagent, and the organolithiums are getting to be less common. And it has a lot to do with the fact that while we do make these, when these two react, they actually kind of react like standard old nucleophiles, and they have all those same restrictions, as in a branched and bulky nucleophile can actually cause some steric hindrance. And since these will be relatively strong nucleophiles, these are going to favor SN2 type reactions. So it's hard to do a substitution if you're actually trying to attach a tertiary location. So the coupling reactions, the electrophile we attack, the Rx that this thing will come and attack, there's going to be some kind of limitations on this. It really can't be tertiary, because there's too much hindrance there. So think of these two, the magnesium and lithium, makes very good nucleophiles, but their bulk can be a limiting factor. All right, the next ones actually avoid some of that. The next few coupling reactions can kind of avoid some of these problems. But right now we have to worry about steric hindrance and the fact that they're not super stable around certain things. Like all of the ones we saw, the organolithiums and the Grignard reagent, if you have any one of these functional groups as a solvent or even on the molecule, so if they're anywhere in the pot, they will react with that Grignard reagent and destroy it. Now that might be a desirable feature, because here's something kind of cool. This bottom reaction, it seems like this would be bad, but think about it. So if I have a bromine on it, I can turn that into a Grignard reagent, and then if I just put this in the water, I lose that magnesium bromine. Now, that might seem undesirable, but it's about the only way, or it's an easier way, to turn an organohalide back into an alkane. Now, what we end up doing in many cases, deuterium is something that shows up differently and changes some. It behaves chemically exactly like a hydrogen, but it will actually hide in things like NMRs. So we actually use this technique to mark certain locations sometimes, because this would put a deuterium that's hidden, it's like a hidden hydrogen, where a bromine was. Now, the magnesium bromide here ended up with the OH. So another product on both these was MgBr and an OH, or a OD for the deuterium one. All right, but this type of thing happens with any one of these. These guys all kind of attack that magnesium bromine, and the magnesium ends up with these, and there's like a H left on. So it destroys the Grignard reagent. Just that might be a desirable outcome. But it does limit what we can put in the pot. Typically our Grignards and the organolithiums, you're doing those with just straight alkyl halides, and you're reacting them with pretty much straight alkyl halides. So just RXs and RXs. All right, the next one we're going to look at, Gilman here, just creates a heck of a lot more stable environment. The THF is a little bit nicer to work with, and gives us a little bit more versatility. So what we're going to do to make a Gilman reagent, which is this organocuprates, we're going to take an organolithium and add copper iodide to it. Now specifically it's copper 1 iodide. And as long as it's copper 1 iodide, we make this organocuprate, which is our R group, whatever was with the organolithium, and it's going to be attached to a copper lithium. And it turns out the Gilman reagents will react a little bit easier, and they're a heck of a lot more shelf stable. They don't actually get destroyed immediately if they get in contact with some of those acidic nucleophiles. All right, coupling reaction of this nature. We're all seeing these with just an RX, so an organohalide, but we're showing that that organo point can be almost anything. And there really isn't too many limitations here. Now, on the magnesium and lithium, since that's a lot more like SN2, there's no way this would have actually worked with a Grignard reagent or the organolithium, because we can't do a backside tack on a vinyl position, and we definitely can't do it on a ring. So the fact that the Gilman reagent reacts with these adds us a cool little benefit. So we can make a coupling reaction on locations that were harder to do with organolithium or organomagnesium. Now, the other plus, for the most part, it's safe to say if you have a very stereocenter specific location, so see how the CH3 and the bromine PR was opposite, that new group is going to go exactly where the bromine is. You don't have to worry about that double bond moving. So it keeps the stereocenter intact. All right. Yeah, that's what this was, keeping the stereocenter intact. So if we have more like a cis or more like a trans, the new point is still the same thing. It keeps that stereocenter. All right, the next one we're looking at is a lot newer. So Suzuki reaction and the next one, the Heck reaction, are all discovered in the 90s, I think it was. The two guys that did those shared a Nobel Prize with a third person for these type of reactions in 2010. So these are newer. But where this comes in quite handy is it's very similar to the organocuprates, but much, much higher yields. So organocuprates, that was the ones we just did. This could have been any RX, and this is another R attached to a copper lithium, and you just actually attach those two R groups, this R and this R. Actually, I'll do a double prime to actually make them distinguish. And we just made a new RR bond. All right, well, Suzuki does the same thing, but still have an organohalide, but instead of the organocuprates, it's an organoboron. Now, boron being less electronegative than carbon, it still makes this somewhat nucleophilic, but it gets really high yields. Now, PDL2, palladium with at least 2 ligands on them that are exactly the same. The reason it's listed this way is it turns out that what is attached to ligands can vary. Suzuki found early on that you kind of wanted ligands that could take oxygens, but or have a place to absorb oxygens. So the ligands just needed to have space on them to absorb stuff. There was a huge amount of variety here. There's a lot of things that work. As a matter of fact, a lot of the more common palladium ligands actually have 4 of those exact same thing on there. So it's PDL4. But it needs to be a PDL2, and you are perfectly allowed to just do L2. You don't actually have to define the ligands. Matter of fact, I don't even think your book shows any of the suggested ligands. But keep that in mind. The reason they don't is because since this is new, and real new by comparison to some of the stuff in organic chemistry, we're still making this stuff better. So what the actual ligands are in the real world is still evolving, and they're getting better and better and better. And we'll see that in a bit in a later reaction. All right, but this does a very similar idea of what we just saw with the organocuprates. It just gets us a higher yield. Now, the other neat thing, the organoborates can be anything. So the organocuprates needed to be something we could make an organolithium out of. Now, we could do just about anything, but the organoboron we can make almost anything out of. So this R can be just about anything, and this R can be just about anything. And the Suzuki reaction, the new bond that's formed, has the same stereochemistry that both of these species had. So our organohalide is likely to have a very specific orientation. It's going to stay that way. So we don't get any rearrangements of the stereocenters. If it was cis, it stays cis. If there's an R and S somewhere in the molecule, it stays R or S. So a lot of versatility on this. Very good, usable reaction. Well, the next of these new ones, done by Heck, it's still high yields, but what we're changing now is our, instead of having an organoborate type thing, it really is just a halide with a vinyl halide or an aryl halide. So it's just a halide near a double bond. Now, similar palladium-based catalyst, but now we'll have this triethylamine, and we're going to create a new bond. But here's where this one's neat. It turns out it's the hydrogen that's on a vinyl position that gets replaced by the R group. So it's not a nucleophile or a halogen that leaves. It's actually a hydrogen. So the Z group there stays exactly whatever it was. So very high yields, a lot of versatility, still palladium and a ligand. All right, examples of this one to see what the heck we're talking about with that. If you notice, there is nothing very special about this. It's nothing but carbons and hydrogens. But they're all four hydrogens are vinyl hydrogens. So when we get our organohalide in there and that palladium ligand and the triethylamine, we essentially rip off one of those four hydrogens and attach that where the bromine was. And same thing happens here. See how our backbone zigzags where that iodine is? Well, this iodine is going to come off, and we're going to pull off this hydrogen, the hydrogen that's away from that big group. And that is going to be connected right there, so we keep that trans double bond going. You don't have to worry about it rotating or rearranging or becoming one of them cis. It's going to stay trans. Very predictable behavior in the heck reaction. That's a heck of a reaction, huh? I had to say it. All right. Now, before we do this alkene metathesis, I think we should have done something on this kind of different in our textbook. So I'm going to add just one little blank page here. And the reason I'm going to do an extra page, did it actually add it? I'm just seeing a flash of a screen. No, it didn't add it. See, I don't know how to add a screen apparently. Or I'm not, there, okay, there it goes. It just not actually clicking right. Now, the reason I brought this up and the reason I want it bigger, I don't know why that actually, oh, because it rotated. How do I rotate this page? I can write on this. All right, the reason I actually wanted to do this is because if we're talking about Heck and Suzuki in this chapter, it'd only be fair to talk about the last guy that was in that group that got a PhD along, or got the Nobel Prize along with it. And I think that's the right spelling from his name. Now, he's a Chinese gentleman, but gosh, he came to America in the 60s and went to Purdue for a postdoc, and he, after finishing up with Purdue, I think he was at Syracuse, but he's been back at Purdue, so he's been in Purdue or Syracuse since the 1960s and been producing a lot since. Well, his reaction, very similar coupling reaction. You have an RX, so an organohalide, and what he reacted it with. So we had the organoborates, organocopper lithiums, the Gilmans. His metal of choice is actually zinc and a different halogen. Now, still another palladium ligand catalyst, but this one, instead of palladium, you could have used nickel. And I think that one, there was variable amount of ligands on there. But the zinc was the difference here. Now, yields were not nearly as high as the other guys, but the nickel could kind of be neat because while the palladium guaranteed you kept the stereocenter, the nickel would sometimes allow it to not so much reverse, but you'd get like a racemic mixture where you'd get both, like cis and trans. So it introduced it a little bit of a different, it would make mixtures, but you had some flex there. Now this one's weird, even though it's zinc, which is abundant and relatively safe, these particular organometallics were reactive towards the air. So if you're doing this, you have to watch out for the atmosphere reacting with your substance. All right, so did that. Our last one we're talking about in this chapter, our last type of coupling reaction, it seems like it seems different, but it is a coupling reaction. It is you're making a new RR bond. It just so happens that if you get double bonds near each other, what kind of happens when metathesis happens is we get a temporary attraction here. Well, that temporary attraction allows these double bonds to move, and so what kind of happens, and I wish they'd drawn this picture differently, because what's kind of happened is a new double bond formed here and a new double bond formed here, and those broke. And that's what they're showing is happening here. And if they're asymmetrical like this is, you might not even see that anything happen because the R's are still attached to that. But metathesis, just think of it, and your possibilities that happen, you just take your double bonds and arrange them so they almost form, actually, get rid of that. They almost form a square, and then the double bonds move. They move around. And it happens when we use this thing, and we're just going to call it a Grubbs catalyst. We're going to talk about that why in just a bit. But a Grubbs catalyst, what we would do to figure out what's going to happen is we are going to just take a duplicate molecule, redraw it directly like underneath it, and then draw a new bond. And I'll just go ahead and do it double, different color ink, and then X out those. And that's how you're going to figure out what it does. It actually makes that metathesis happen. It creates new molecules. Now, there are plenty of possible things that happen, because if you think about this, I could actually have some kind of messed up craziness to happen. So there can be a lot of randomness to this, but we're just moving that double bonds around some. Now, we're going to be fine in anything that we say just to say Grubbs catalyst. The reason that is because they always are, there's always experiments going on with a new catalyst that works like Grubbs does and makes it a little bit faster. And I think I have a slide here, I have Wikipedia here, to see the latest and greatest Grubbs catalyst, just to put that in perspective. Apparently I can't. There it is. All right, so the earliest form of Grubbs catalyst, or a Grubbs catalyst, was this thing with ruthenium, had a chlorine. We've seen this phosphorus triphenyls before. So we have those, and then we have this long chain with more phenyl groups. This is a relatively big molecule, but that was the first catalyst that did this. The most up-to-date modern one, and yeah, third generation, is, yeah, it's either this or this. So this is how it's going to come in a container. So you'd probably buy this, but then you put some of our nitrogen ring in there, and it will make it into a solution. And that's the actual catalyst now. So it still has that ruthenium, still has the two chlorines, but has these bulky groups, and somehow that catalyzed this metathesis. And this particular one is 4 times faster than the previous generation, which was like 10 times faster than that first one I showed. So in the actual chemistry lab, we're getting actually much faster. And I don't remember, this is not that old. I think it had a date on there. So 22. Yeah, 2010, and 2010 would be that latest publication. So that's not even really that old of a time. So and there's still plenty of people working on this, so it wouldn't be terribly surprised if there's even better one out. So that's something we're getting on some newer stuff in organic chemistry, is these coupling reactions, but they actually give us a lot of versatility. Now, we will see these on our test, but you're not expected to know what the catalyst is. You really can say Grubbs catalyst and just do that metathesis. All right, thank you very much. That actually finishes up this chapter.